Now we're going to derive an integrated rate law for case 3, where the reaction order is 2, n equals 2. Another way of saying that is for a second order reaction or a reaction with second order kinetics. So when n equals 2, the rate of a reaction, and as always, I'm talking about a generic reaction where we have some reactant, which I'm going to call A, going to products. The rate of the reaction, monitoring the decrease in the concentration of A with time, for a second order reaction is going to be equal to the rate constant times the concentration of the reactant raised to the power of 2, okay, because n equals 2. Now, I want to once again rearrange this equation by collecting all of the terms with A on one side and then integrating both sides. So I'm going to collect all the terms with A on one side so that I get dA over A squared, and I'm going to move the negative sign to the other side, so I have K times dt. Now that I have organized these terms, I can integrate both sides of the reaction going from 0 to time t. And as I integrate both sides of the reaction, once again, if you haven't had integral calculus, don't worry about the integration. We are aiming to derive an equation that you can use algebraically here. So the integral of 1 over x squared is going to be 1 over x, right? So this is 1 over a at time t minus 1 over a at time 0. And that will be equal to kt. And what I did there was switch the sign around to the other side. This is a useful form of the equation that you can use algebraically. This is the concentration of reactant A at time t, and A0 is the initial concentration. So I'm going to rearrange this to get it into the form of y equals mx plus b because I'm interested in getting a graph with a straight line. So here, x is going to be t, and I'm going to make y into 1 over a. So I'm going to say that 1 over a equals kt plus 1 over a0. And all this is a rearrangement of that equation from up there so that I get it in the form of y equals mx plus b. Of course, the reason I'm interested in doing that is so that I can get an equation with a straight line. So let's set up some Cartesian coordinates. And I am going to plot my y on the vertical axis. And of course, here my y is going to be equal to 1 over the concentration of A. My x is time. So a straight line here is going to have a positive slope that's equal to k. So what my, oops, that's not the nicest straight line. So what my reaction looks like is the reciprocal of the concentration of reactant A is going to be increasing as a function of time. So this equation tells us that a second order chemical reaction gives a plot of 1 over A versus time with a straight line with a positive slope. And that slope is equal to K, right? Because you can see here that K is equal to M. So the slope is equal to K. This is different from what we saw with the zeroth and the first order kinetics because there we had a slope equal to negative K. Here the slope is equal to positive K because we're dealing with the reciprocal of the reactant concentration. The intercept, B, is going to be equal to, oh, I forgot up here. This should be 1 over A0. All right, let me make sure I didn't, okay. So that should be 1 over A0. The intercept is 1 over A0. what does this graph imply about the concentration of reactant A with time? Well, as time goes on, the reciprocal of the concentration increases, which is like saying that as time goes on, the concentration of the reactant decreases, right? If the concentration of the reactant is decreasing, its reciprocal will increase. So we get a plot with a straight line by plotting the second order equation in this form that we see here. Now, let's derive an expression for the half-life for a second order reaction. As you will recall, the half-life, which we can abbreviate as T sub 1/2, is the amount of time it takes for the concentration of the reactant to be cut in half. So when the concentration of A is equal to 1/2 of what it was at the beginning. Let's take this and plug it into the expression for the integrated rate law that we have up here. Okay, so we want to take that 1/2 A0 and plug it in. So if I put 1/2 A0 on the left side, and that's going to be equal to K times T, and then in this case, the T is specifically T 1/2. The intercept is still 1 over A0. So I can collect the terms of this on both sides. Wait a second. I think that actually the 1/2 is in the numerator now because it's in the denominator of the denominator. When I plug it in here, right, it gets in the denominator of the denominator. So the 2 actually ends up in the numerator. Let me simplify this a little bit. 2A0 minus 1A0 is, okay, so hang on a second. The 2 is in the numerator, and the A0 is in the denominator. That is from plugging in this into the denominator here. Okay, so the A0 ends up in the denominator and the 2 goes into the numerator. All right, I'm getting it. We got it. Now, let's simplify this. 2 over A0 minus 1 over A0 is going to give me 1 over A0 is equal to K times T 1/2. Rearranging to solve for the half-life, I get a T 1/2 equal to 1 over K times A0. This is the useful expression when I want to calculate the half-life for a second order reaction where n equals 2. All right, so now it's very useful to have a summary of 0th order, 1st order, and 2nd order kinetics. So on Blackboard, I have put a handout that looks like this. Okay, you can download this handout on Blackboard adjacent to this video. Here we have all of the information we need kind of distilled into one page for 0th order kinetics, 1st order kinetics, and 2nd order kinetics. This is all of the integrated rate law information. So everything that I've talked about in the last 3 lectures is distilled into one chart. First, we can talk about the differential rate law. Okay, that's kind of even going back to the beginning of this chapter. So we have the differential rate law when n equals 0, n equals 1, and n equals 2. The concentration of reactant A with time is always going to be decreasing. But when there is no dependence of the rate on the concentration of A, we just have a kind of linear decrease here. This decrease in concentration is 1st order, and then we get a much steeper slope when it's 2nd order. right there, a much kind of steeper decrease. The integrated rate laws that we derived are summarized for you here in various forms. Okay, this is the natural log here. They give it to you with both the E and with the natural log. That should be ln, not 1n. There's a little weirdness in the font there. Here are the straight line plots. So the reason why I was always putting it into the form of y equals mx plus b, putting the integrated rate laws into the form of y equals mx plus b, is so that we could plot it with a straight line to figure out the rate constant. So for 0th order and 1st order reactions, the slope of the straight line plot is equal to negative k, the negative rate constant. And for the integrated rate law for 2nd order reactions, you plot 1 over the concentration and the slope is equal to positive k. Right, that's useful in certain problems. The relative rate versus concentration shows what happens to the rate when we double or triple the concentration. So for 0th order kinetics, if we double or triple the concentration, there's no effect on the rate because the rate does not depend at all on A. The rate is only equal to the rate constant. Whereas for 1st order kinetics, if we double the concentration of A, we double the rate. If we triple it, we triple the rate. For 2nd order kinetics, we have a square, right? The rate is equal to k times the square of the concentration of A. So what that means is that when we double the rate, when we double the concentration of A, the rate goes up to by an extra factor, right? Because it's 2 squared. If we triple the rate, it's 3 squared, so the rate would go up by a factor of 9. So then we have the expressions for the half-life, which we derived. And finally, for the different kinds of kinetics, the rate constant k has different units that come out of the equations. So in the next lecture, we'll do a couple of examples where we apply integrated rate law information.